A common reaction that you'll see with alkyl halides is a nucleophilic substitution reaction. In this type of reaction, a leaving group, in this case the chlorine, is replaced by a nucleophile, in this case a thiolate. The reason that alkyl halides can undergo such a reaction is because the chlorine, or the halogen in this case, has a dipole. It's electron withdrawing. Because it's pulling electron density away from that central carbon, this alpha carbon, we will generate a partially positive charge on the carbon and a partially negative charge on the chlorine. This partial positive charge will have an attraction to the negative charge of our nucleophile. So let's assign the different components of this reaction. You have a substrate, in this case the isopropyl chloride, with a leaving group, the chlorine, and you have a nucleophile. We call this a nucleophile because the nucleus of an atom is positive. A nucleophile is attracted to positive charge. We can simplify one of these reactions just by writing Lg in place of whatever leaving group we have, and Nu in place of the nucleophile. Just keep in mind that for a compound to be nucleophilic, it has to have a lone pair of electrons that we don't always draw. In the case of the thiolate here, we did not draw in 3 different lone pairs. So how does this reaction actually work? There are 3 plausible pathways. First, the nucleophile, with its lone pair, can attack that partially positive alpha carbon. If this happens, it forms a new bond. So let's draw our new molecule here. We have the nucleophile with a new bond to the alpha carbon. We have a methyl group, we have a hydrogen, we have another methyl group, and we have the leaving group. What you should notice right away about this molecule is that this central carbon is making 5 bonds. So even though we can draw an arrow, it's not realistic to suggest that this is the mechanism or the pathway that the reaction will proceed. Let's think of a different mechanism. Instead of having a bond form alone, what if a bond formed and at the same time we broke another bond? This way the carbon will only have 4 bonds in the end. If we redraw the products here, we have our leaving group replaced with the nucleophile, and our leaving group with a lone pair now has a negative charge. This type of reaction is called bimolecular. It's bimolecular because it involves 2 molecules colliding for the reaction to proceed. It's also concerted, which means that as this new bond is forming, another one is breaking at the same time. If we can describe a reaction as concerted, we can also describe it as stepwise. This is the 3rd plausible mechanism. What if we broke a bond first? In this case, what if the leaving group just comes off? If it does, we'll be left with a carbocation, which is a positive charge on carbon. We are going to lose the leaving group. Just write minus Lg so we don't have to draw it. Then the negative nucleophile can be attracted to the carbocation. So in this case, we make the same product as up here, but in a stepwise fashion. This is a stepwise mechanism, and it is unimolecular, which means the rate depends only on this first step, which involves 1 molecule. Later on, we're going to talk about what differentiates a bimolecular versus a unimolecular mechanism, but for now, let's talk about the specifics of a bimolecular reaction. We call a bimolecular nucleophilic substitution reaction SN2 for short. S for substitution, N for nucleophile, and 2 for bimolecular. There are 2 molecules reacting. The rate of such a reaction is based off of some constant and the concentration of the substrate and the nucleophile. So, take our example here. We have a thiolate as our nucleophile. We have a substrate with a leaving group. The thiolate will attack the carbon here and kick off the chlorine, giving us our products. What does this actually look like? First off, you have to account for the fact that this chlorine is partially negative because it's electron withdrawing. It's relatively electronegative. Because of this, the negative charge of the thiolate is going to stay as far away from that negative charge as possible. Like charges will repel each other. So in an SN2 reaction, we follow what we call a backside attack. The thiolate has to approach from the opposite direction as the leaving group. So let's redraw this a little bit. Let's draw our leaving group as flat right here. Let's draw in our methyl group and the hydrogen that we don't normally draw in. For a backside attack to occur, the thiolate has to approach opposite from the chlorine and kick off the chlorine group. This type of reaction results in a transition state where the bonds are forming and breaking, but they haven't fully formed or broken yet. In this case, as the thiolate approaches, it's going to force the angles of these three groups to change a little bit, so that instead of being tetrahedral, they're going to be more trigonal planar. So that methyl group will be straight down, this methyl group will be coming straight towards you, and this one will be going straight backwards. At the same time, we have our chlorine bond beginning to dissociate. We have a new bond between the sulfur and the carbon forming. Because the chlorine-carbon bond is dissociating, this chlorine is now partially negative. The thiolate is partially negative because it's donating electron density to that carbon in the center. Because this is a transition state, we'll draw brackets around it and give it a double dagger. When the reaction is finished, we will be left with a new bond between the sulfur and the carbon, and we're going to continue moving these bond angles a little bit more to the right. So we've got our one methyl group down here, the other one is now up and to the right, and the hydrogen is up and to the right. So we go from a tetrahedral shape to a tetrahedral shape with this trigonal planar intermediate. Let's talk about the energy of this type of reaction. For a reaction to proceed, the energy of the products has to be lower than the energy of the starting materials. So let's draw in our products again. Okay, and we'll make a graph. This is called a reaction coordinate diagram. We have the potential energy on the y-axis, and down here on the x-axis we have what's called the reaction coordinate, how far the reaction has gone. Let's pick an arbitrary energy for the starting materials. We'll say right here. And again, for a reaction to proceed and be exothermic, the products have to be lower in energy. So let's draw them down here. We'll label starting materials here, products down here. What happens in the middle? We know that during this reaction, we have a transition state, which I drew previously. This transition state, we're breaking a bond which takes energy, but we haven't formed a new bond yet, which will give us back that energy. Because of this, the transition state is going to be higher in energy than both the starting material and the product. We'll put that up here. So if we draw a curve, we go up in energy to the transition state. As the product is formed, it's more stable, we get energy back. The energy gap between the starting material and the transition state is our activation energy. Some reactions we need to heat up to get to proceed, others will react at room temperature. You may have noticed that SN2 reactions reverse the stereocenter that we were looking at. So again, let's take a look at this example. The thiolate will attack here, backside attack, kick off our chlorine. Let's draw our transition state. We have an SH, new bond forming. We have our ethyl group straight down, methyl group up and to the left, hydrogen straight back, and our chlorine is leaving. That's our transition state. Notice the thiolate is going to be on the opposite side as the leaving group. So if we draw our product, what we'll see is this molecule here. So again, the sulfur is on the left in this case compared to our starting material, which was on the right. So if we want to draw it where the nucleophile is on the right side of the molecule, we'll flip the whole thing over. If we do that, the ethyl group is now on the left, the SH is on the right, and this methyl group, which was pointing towards you originally, flips over to the other side. It's now on the back. So the product of this reaction will have the methyl group with the stereocenter reversed. So it was a wedge, and now it's a dash. And that is a direct result of the backside attack of our thiolate, or our nucleophile. This does not necessarily mean we're going to change from R to S. I'll give you two examples here. The first one was the example that we just did. Let's assign the stereochemistry. 1, 2, 3. This is R. Our product, we know, reverses the stereocenter. So this will go from a wedge to a dash. Again, let's assign the stereochemistry. 1, 2, 3. This would be R, but the methyl group is back, so it's going to be S. In this case, we reverse the stereocenter, wedge to dash, and we also reverse the configuration from R to S. Let's take a look at another example. Assign the stereochemistry. 1, 2, 3. In this case, we start off with R. If we replace the leaving group here, and we invert the stereocenter, let's take a look at the stereochemistry here. Now, instead of the SH being the highest priority, it is the S-ethyl group, because ethyl is larger than hydrogen is. So this is 1, 2, 3. So this goes counterclockwise, but it's backwards. So this will actually be R. So even though we inverted the stereocenter from a wedge to a dash, we went from R to an R. The reason this happens is because the R and the S configuration is a construct of organic chemists. We sort of just made rules to determine whether something is R or S. Nature isn't really concerned about R or S, or that we decided that the higher molecular weight should always be first. So, when you're assigning the stereochemistry of these types of problems, you have to remember that you'll always invert the stereocenter, again wedge to dash, but you might not change from R to S. Finally, let's talk about the size of the substrate. It can actually limit the rate of SN2 reactions. So let's take this methyl chloride. If we drew a ball and stick model of this molecule, chlorine is in green, it's going to be partially negative, our central carbon is partially positive, and we know that the nucleophile will approach from the backside. Hydrogen isn't very large, so there's lots of room, it's easily accessible to get to the backside. So in this case, this is a very fast reaction. What happens if we replace one hydrogen with a methyl group? Well, ball and stick model, all of a sudden this hydrogen here is much larger. This adds more steric hindrance. Steric just means size or bulk. So if we're approaching the backside again, there's a little bit of a clash between the nucleophile and that one methyl group. So that will slow the reaction down. What if we replace two hydrogen atoms with methyl groups? Again, let's take a look at the ball and stick model. There's even less space now. So if we're approaching from the backside, we have steric clashes from this methyl group and this methyl group. This reaction, where you have a secondary substrate, will be the slowest. Why do I say the slowest? Well, if we look at a tertiary substrate, there's just no way for our nucleophile to fit into the backside. There's too much steric crowding. So in terms of an SN2 mechanism, we will never have a tertiary substrate undergo an SN2 reaction.